Hi.
Hi, Misha.
Hi, Pilaud. How are you doing?
Not too bad, thanks. And you?
Yeah, I allow to share screen now. So if you want to check anything, so.
Okay, let's see if this works. Should
Yeah,
we share
great.
now?
Yeah.
Okay, super.
Everything is working.
And it's moving when I do that.
Okay. Hi, everybody. So we are happy to have today Pierre-Guy Plamondon, who will speak about something about associahedra. Yeah. And yeah, please, Pierre.
Thank you very much for the introduction and for the invitation. I'm very happy to speak in this Cluster Algebras virtual seminar. I've never been in Michigan before, and I don't know if this counts.
Well, okay. I think it's understood. Accepted.
Okay, I'll say that I've been in Michigan from now on. Let me share my screen. There we are. Oops, okay, there we go. So what I would like to talk about is realizations of associahedra, or I should say generalized associahedra, and the relation with minimal relations between G vectors. Now this is a report on a joint work with 3 people, Arnau Padrol from Sorbonne Université, Yann Palu from Amiens, and Vincent Pilaud from CNRS and École Polytechnique. So what I would like to start with is maybe an example, a small example, maybe the smallest non-trivial example in cluster theory. So motivation, we want to realize associahedra. I'll say exactly what I mean by this in a moment. So let's, before I draw the picture, our example is an example in type A2. So you start with a quiver with 2 vertices and 1 arrow like this. And then in a cluster algebra seminar, I think it's safe to assume that most of you have performed the computations of cluster variables, G vectors, and so on in type A2 about 3,000 times. One thing that happens is the G vector fan. So let me draw the G vector fan. There are 5 cluster variables, so 5 G vectors. And the G vector fan is in 2 dimensions, and it looks like this. Now the actual G vectors, we can also draw them. They're all vectors in the unit cube. My drawing is not so good, but I can at least give the vectors. This is 1, 0. This is 0, 1. This is -1, 1, -1, 0, and 0, -1. These are the G vectors of the 5 cluster variables in type A2. Now we can use this picture in order to realize the associahedron in type A2. So the associahedron in type A, this is a famous polytope that was introduced in 2 different ways, by Tamari in 1951 and also by Stashev in 1963. Oops. And you can geometrically realize it on this picture. And the way you do this is that you draw a polytope such that the G vector fan is the normal fan of the polytope. So let me draw one example like this. You can do it by hand very easily on this picture. Like so. There we go. So it has, so the associahedron has geometric realization. This is what we'll be looking at today. I should point out that these realizations appeared in various steps and using various tools. So in 2002, using the D vector fan, not the G vector fan, but the D vector fan, Chapouton Fomin and Zelevinsky realized generalized associahedra for any finite type cluster algebra, but with initial bipartite seed. And then in 2011, 3 other people, Holweg, Lange, and Thomas, realized them using Cambrian fans for any acyclic seed. And finally, using G-vector fan, just as I've done in this picture, for any initial seed. This was done in 2018 by Holweg, Pilaud, and Stella. So any initial seed, always in finite type. So what is our game today? Our game is to try to understand all possible ways to realize the associahedron using the same G-vector fan. And what I want to point out is that the picture I've drawn, you could have done it in many different ways. I mean, here's another realization of the associahedron. It's another perfectly valid realization. Here's another. There's a lot of them. They have different shapes, they have different forms, and we're interested in the space of all realizations of the associahedron. So let me just put some setting. At first, we're gonna be interested in. Oh, maybe I do this afterwards. Okay, so we are interested. Excuse me. We are interested in the space, whatever that means for the moment, in the space of all realizations of the generalized associahedra. I'll define precisely what this space is and what I mean by realizations just in a moment. But maybe why were we interested in this? It's because the question arose in work by physicists. So in 2018, in a work by Ahkani Hamed, by He and Yann, they described this space for any linearly oriented cluster algebra of type AN. So they described this space for a quiver of type AN in this way. And this was shortly afterward generalized by another team of 5 people from Montreal, Baziemat, Douville, Moussavand, Thomas, and Yildirim. They generalized this to any Dynkin type and any acyclic seed. Any acyclic initial seed, I should say. So my aim today in this talk, and our aim in the work with Arnau, Yann, and Vincent, was to generalize this construction of the space of all polytopal realizations of the generalized associahedron for any Dynkin type and any initial seed. So generalize to any Dynkin type and any initial seed. And what I should mention is that our approach is different from the ones that were used before. So using a different approach. Our approach is such that we don't need to, or rather, we can treat all initial seeds and all Dynkin types in the same way. So there are two ingredients in our approach. The first one is the type cone of a fan. And I will define this for maybe about half of the talk. I'll be talking about type cones. Type cone of a fan. And the first half of the talk will work for any polyhedral fan. So I won't be really looking at G-vector fans of cluster algebras, but they will come back later. After all, this is a cluster algebra seminar. And the second ingredient is a categorification of G-vectors using extrangulated categories. Now today, I want to talk about type cones. And I will not really, despite what I've written in my abstract, I will not really touch upon categorification of G-vectors. While preparing the talk, I had to decide between talking about categorification or drawing a nice picture, and I decided that I wanted to draw a nice picture. But I don't have time to do both.
Excuse me, Pierre-Guy.
Yes.
So just to understand, so your result is exactly the same as well, this group kind of Bézier, David, yeah, because acyclicity is kind of empty in this situation for Dynkin type, right? Or you also included a affine case.
No, we don't include the affine case, and this is maybe an important point, and I should, maybe at the end of the talk, I'll try to comment on this. The affine case, the infinite types are much harder to work with because, well, the polytope is not a finite polytope, or it's not defined by finitely many inequalities.
Oh, no, but sorry, yeah, I take it back. So you might have different seeds, more seeds than
yes, exactly. So it's not so what we add using this approach is that we can have a cyclic initial seed.
I see.
And look at G-vectors with respect to those. And maybe what I should say is that our approach doesn't really care whether the initial seed is cyclic or acyclic. It treats all of them in the same way.
Mm-hmm.
Okay, so let's talk about type cones, and let's define everything properly. So I'll be working with F a fan, but I want it to be better than just a fan. So it's going to be an essential, complete, and simplicial fan in Rn. So what is a fan? A fan is a union of cones such that the intersection of two cones is also a cone of smaller dimension inside the fan. And these words that I've written here, essential means that 0 is a cone. Complete means that the fan covers the whole of R small n. And simplicial means that cones are simplicial. What does it mean for cones to be simplicial? It means that their rays are linearly independent. So if you're in 3 dimension, something like this is simplicial, but something like this is not. Yes, all 4 rays in this drawing and on the right are necessary in order to generate the cone, but the cone is 3-dimensional, so this is not simplicial. Okay, so when you have this, we're going to look at, maybe I should say F has finitely many cones. In all this talk. So it's not necessary for a fan to be finite. And in general, let's say outside of this talk, I would prefer for fans not to be finite, but inside of this talk, I will insist very strongly that they are finite. Okay, so since it's finite, it has finitely many rays. Knowing the rays is enough to know the fan if you're in 2 dimensions, but it's not enough in general. You have to know what the cones are. But knowing the rays is a lot of information. So let's choose generators for the rays and let's organize them in the matrix. Let's G be the matrix whose, let's say, big N rows are generators of the rays of the fan F. So if you go back to the example we had earlier, the example in type A2, G would just be this matrix. You have 1, 0, 0, 1, minus 1, 1, minus 1, 0, and 0, minus 1. These are generators of the 5 rays of this cone. And I'm using the word G, of course, because in the case of cluster algebras, the rows are the G vectors of the cluster variables. Okay, now I'm interested in having a realization of the generalized associahedron. What do I mean by this? So what I will call a polytopal realization of the fan. So polytopal realization of F. Well, it's a polytope whose normal fan is precisely F. So if you remember the example above, so maybe I don't like doing this, I'm sorry, but if you go back to the picture, you see 3 different polytopal realizations of the G vector fan in type A2. Now, what happens on this picture is that in order to define a polytopal realization, all I had to do was choose heights on each ray of the G vector fan. And then I just have to look at the hyperplanes defined by these heights, sorry. So I have a set of inequalities, and then the generalized associahedron, this polytopal realization, is just the intersection of all these half planes given by a bunch of inequalities. But if I'm not careful, and then I'm going to go down, if I'm not careful, maybe I do this example again here. If I choose the heights not carefully, maybe I choose this and this and this and this, and then I choose a height here that is very far away, then all my inequalities, they define a polytope, but it's not a polytopal realization of my fan. Yeah, this ray here is not normal to any of the faces of this polytope, so that's not okay. So for any, now let's formalize this. For any choice of heights on all the rays, so for any H, a vector in R big N is the number of rays in my fan, define the following thing. Define P of H. Well, it's the polytope defined by the inequalities given by H. If H is chosen carefully, then P of H is a polytopal realization of the fan. If H is not chosen carefully, then it might be something like this drawing here, and it's not a polytopal realization of the fan. So what we want to describe is the space of all H's such that P of H is a polytopal realization of the fan. And this is what Macmillan in 1973 called the type cone of a fan. So the type cone of the fan F is the following set. TC of F, TC for type cone, the set of all H's in R big N such that P of H is a polytopal realization of the fan. And this is what we want to describe. So this is what the team of physicists did in type AN, and this led to the question of how could you describe this space in general. So before we maybe look at an example in detail of what this is, let me list a bunch of facts about the type cone of any fan. First, it's a cone. So the name is not chosen at random. It's actually an open cone. So TC of F is an open cone in R big N, and we call big N is the number of rays. Secondly, it contains a linearity space. It contains something big that's not very interesting. And by this, I mean that if you just look at the type cone and translate by any vector in here, recall that big G is the matrix whose rows are the rays of the fan. So the G vectors, if you're in a cluster algebra, this is exactly the same as the type cone itself. So it contains a space that's not very interesting, this G times R, and it's often useful to project on the smaller space to get rid of it. So it's often useful to project to a smaller space to get rid of this linearity space. Okay, good. So it's a cone. The type cone is a cone. How can we define it? So a cone in Rn will be defined by inequalities as well. I mean, you have facets which are given by inequalities, and we want to maybe describe them. And it turns out that we can do it. And the way to do it is as follows. Imagine you have in your fan F, you have two adjacent cones. So let's imagine you have a cone like this. F is simplicial, so in 3 dimensions cones look like simplices. And imagine you have an adjacent cone like this. So these two cones differ only by one ray. So maybe this one is small r and this one is small r prime. So if you have such a situation, so if r and r prime are the sets of rays of two adjacent cones, in your fan, so they differ just by one ray. So let's say that r minus small r is the same as big R prime minus small r prime. Then if you have something like this, I mean, it's clear that these 4 rays in the picture, they're linearly dependent, right? I mean, these 3 are linearly independent. The fan is simplicial, but if you had a 4th one, it's going to be linearly dependent. So you have a linear dependency with them. So let's write one. So let's say that alpha big R prime of small r, this is a scalar times the vector r plus alpha r prime, small r prime times r prime, plus the sum for all those s's that r and r prime have in common of some scalars times s. Let's say that this is 0. And you can normalize this in such a way that alpha r prime of small r and alpha r prime of small r prime are positive. Okay, so if you have this situation, it took a while to write down, but it's really simple. Yes, you have two adjacent cones. They differ by two different rays. The whole set of rays has a linear dependency, a unique one. You just write it down, you look at the coefficients, you normalize it so that some of them are positive. And then this defines you a wall in the type cone. In fact, the type cone of your fan is the set of all h's in R big N such that if you apply this linear dependency to the coefficients of h, you get 0. And you do this for all pair of adjacent cones in F. So this is a nice description of the cone. You know all inequalities that define it. This also tells you why it's an open cone. Oh, sorry, I said equals 0, but that's not right. You want inequalities. There you go. Okay, so you have, so each of these define each of these, if you write equals 0 instead of bigger than 0, you have a hyperplane in R big N. And with the inequality, you have a half space, an open half space, and you take the intersection of all of those, and this gives you the type cone. Just by looking at this, you can see right away that the type cone is indeed a cone, that it's an open cone, in fact, and you can deduce a lot of properties out there. But now the important point is that when you look at all these relations for all possible pairs of adjacent cones in F, probably you have too many inequalities in order to define your, and some of them are redundant. So let's write two things. This means that the facets of the type cone are defined by these exchange relations. So maybe I should have said that this thing here I call an exchange relation. The reason I call it an exchange relation is because of cluster algebras. Yes, if my fan F is the G vector fan of some cluster algebra, then these relations are the exchange relations of G vectors inside my cluster algebra. So you can recognize the combinatorics, but I don't have to work with cluster algebras in this part. This works for any fan. So the facets of the type cone are defined by exchange relations. So the question now is, which ones? Let me be more precise. I have a bunch of inequalities, one for every pair of adjacent cones. Probably some of these inequalities can be deduced from the others by positive linear combinations. So what I'm looking for here, in other words, which are the exchange relations that positively generate all the others? And in order to really grasp what's going on, I think it's useful to spend quite some time on the example in type A2, because there we can draw everything, we can see everything, and even if what I've written above may look a bit abstract, I mean, it's really clear to see what happens on a small example. So let's look at an example. So the G vector fan in type A2. So Q is 1, 2. Same as before. So it's the other advantage of the G vector fan in type A2 is that it doesn't take a long time to draw on the blackboard or whiteboard, or however I should call this machine. Okay, so what's our matrix with all the G vectors? Recall that it's just, well, generators of these rays. Yes, and then it's not any generators. We really choose them to be the G vectors of the cluster variables. Not that it matters that much, but make things simpler to relate to, maybe. And then you have exchange relations. And the exchange relations, maybe I want to put them all in a matrix. So what will I do with this? So this matrix will have 1, 2, 3, 4, 5 columns, one for every ray. So this will be 1, 2, 3, 4, and 5. Okay. Now remember that your G vectors are normalized. Yeah, they all live in this unit cube. And then you just look at the relations between them. Yes. So if you mutate, if you start, so this often here is the initial seed, and if you mutate at 1 and 1 gets replaced by 3, what is the relation between the G vectors? Well, the G vector at 1 plus the G vector at 3 is equal to the G vector at 2. So if I put a -1 here, this gets 0. Did that make sense? So maybe what I really want to say here is that 1 times the G vector at 1 minus 1 times the G vector at 2 plus 1 times the G vector at 3, this is 0. And then I do this for every pair of adjacent cones. I only have 5 here, so it's easy to write them all. Let's see. So I can mutate 2 into 4, so I get 1, minus 1, 1, 0, 0. Then I can mutate 3 into 5. I can 1, minus 1, 1, 0 everywhere else. Then I could also, if I started from the initial seed, I could mutate in here instead. And what the relation here is just that 2 plus 5 is 0. 2 plus 5 is 0. And then I can mutate across this wall here. And the relation here is just that 1 plus 4 is 0. Okay. So that's my matrix. Now this defines a bunch of inequalities. Yeah. So the type cone of F, according to what we'd written above, is the set of all h's in R5, big N is equal to 5, such that, well, all the lines in this matrix must give you inequalities that are satisfied. So H1 minus H2 plus H3 is greater to 0. And also H2 minus H3 plus H4 is greater to 0, and so on. So doesn't take so long to write them all, so let me just do it. This way it's as clear as possible. Oops, H4. Okay, so this is the type cone according to the above discussion. But then if you think about it, some of these inequalities are redundant. So if I give names to these inequalities, H1, H2, H3, H4, and H5, actually these two are positive linear combinations, or sorry, non-negative linear combinations of the three above. So these are redundant. You don't need them. So these two inequalities are redundant. So you actually only need 3 inequalities to define the type cone. So the type cone has 3 facets. And you can kind of draw it. And here I will attempt the promised nice drawing. So where does the type cone live? It lives in 5-dimensional space. That's a bit big. But remember, there's a linearity space that we can quotient out, and here it has dimension 2. So I can view the type cone in 3 dimensions instead. And then when I do this, I view it in 3 dimensions, and I cut with a hyperplane, so I can look at the projection in 2 dimensions. This is what I'll be drawing. So I'll draw a projection of the type cone of F now, or at least I'll attempt to. So let me draw first a couple of lines, and I'll explain what I'm doing afterwards. And hopefully it will become clear. Okay, so this region in here is the type cone. So whenever you have a point in here, it means that you have an H such that all inequalities are satisfied. Now what's happening here? Each of these lines, oh gosh, I didn't write them in the same order as in my notes. So let me try to write them correctly. So this line here corresponds to the inequality H1 is greater to 0. So this is a half space like this. Now this line here corresponds to the inequality that used to be H4, so that's H2 is greater to 0. So that's something like this. Yes, I'm defining a cone, so I have a bunch of inequalities, and I'm looking at the intersection of the half spaces. H3 defines, where are you, H3? It defines this one here, H3 greater to 0. And then the two other lines are defined by H4 and H5. So let's see. This is H4 here, and this is H5. And if you look at the intersection of all the half spaces defined by these inequalities, you really see that H4 and H5 are useless. They're redundant. You don't need them. Yeah. So what's happening now? Let's take a closer look. Maybe I want to draw it a bit bigger so that we can really see what's happening. Okay, so I'm still drawing the two useless ones. Okay. So when you're in the middle of this picture, you get realizations of the associahedron. So something like this. It means that your G-vector fan is something like this. Yeah? Okay. Now remember, when you're in the type cone, what you're doing is that you're playing with the heights of that you've put on each of the rays of your fan. Yeah. So if you move continuously inside your type cone, what you're doing is that you're deforming your associahedra by playing with the heights at which it should intersect each of the rays. Now, if you say hit this one here, so if you play with this one here, you're playing with this height here, and you're moving it along this ray. If you move it too far, so if you go too far in this direction, if you move it too far, what you get is not a polytopal realization of your fan anymore, but you get something like this. Yeah, it's a polytopal realization of a fan that's a coarsening of your G-vector fan. This is what is associated to this wall here. Now, if you want to know what's happening with this wall, so if you're going in this direction, if you recall, this is the inequality H3, so the one given here. This means that you're playing with the height on your fourth vector, and you're sending it so far away that it doesn't interfere with this, the other inequalities anymore. So what you get is a picture like this. You get something like this, which is again a polytopal realization of a different coarsening of your G-vector fan. And so on. If you go at every boundary, so if you take the closure of your type cone, the type cone is open, but if you take the closure and look at the walls, you can see that what you get are polytopes that are always realizations of some coarsening of your G-vector fan. Oops, that one was not really good, but well, okay. I think you understand what I mean. And there's two missing. There's this one here and this one here. but these are kind of boring. They're flat. This one and this one. Okay, so this is what's happening in this type A2 example. So you've got a cone of choice of heights, an open cone of choice of heights on each of the rays, such that you can build a polytopal realization that intersects each of the rays precisely at those heights. But if you go to the closure, so in other words, if you let me go above, if you choose one of these inequalities here and you transform them into an equality, so if you go to the wall here or here or here or whatever, then you still get a polytope, and it's still a polytopal realization of some fan, and it turns out that this fan is just your original fan with some rays taken off. So it's a coarsening of your original fan. This works all the time. So this is the first theorem of this talk, theorem 1. So the relatively open faces of the closure of the type cone, so the relatively open faces of the closure of the type cone are the type cones of the coarsenings of F, of all the coarsenings of F. So that's the first general result. Now, maybe I want to point out something in this example. In this example, what you get in the end, the type cone is a simplicial cone. It's generated by 3 things, and it's basically 3-dimensional. So in this example here, the type cone is simplicial. So what does this mean? Remember what we're trying to do. We're trying to describe the space of all polytopal realizations of our G-vector fan. We call this the type cone, and now we can describe the type cone, at least in this example, and it's given by 3 exchange relations. Yes. And I guess the final point of this talk is that 3 is equal to 5 minus 2. Yes, the total number of cluster variables minus the number of initial cluster variables. This will be kind of the punchline of this talk. So let me get there a bit later. I want to maybe add as a remark that the type cone of a fan is not always simplicial. So the type cone of a simplicial fan is not always itself simplicial. So the fact that in the example above it's simplicial, that's pretty nice. It doesn't happen all the time. So maybe I can give an example, a counterexample for this. It's a counterexample in 2 dimensions, and it's really easy to draw as well. It's similar to there you go. It's similar to the G-vector fan in type A2, but I've just added 1 ray, so it becomes symmetric. And if you compute the type cone of this, it's not simplicial anymore. And for those of you who like representation theory of quivers, I know you're out there in the audience, this is the G-vector fan of the pre-projective algebra in type A2. So of the algebra given by this quiver and relations. So even for particularly nice algebras yielding particularly nice simplicial fans, the type cone is not necessarily simplicial. Okay, so what do we care about the type cone being simplicial, apart from meaning that its generators are in a number that we, in this this will be the statement of my second theorem. Well, the second theorem of this talk, I mean. This is, again, in this joint work. If the type cone is simplicial, so if it's a simplicial cone, as in the example in type A2, so that means that it's generated by a fixed, sorry, I should say it's defined by a fixed number of inequalities. So we know the facets of the cone. These facets are now given by exchange relations. So let's say, let's put them in the matrix. And if K is an big N minus small n times big N matrix whose rows are the exchange relations defining the facets, of the cone. And then, so this is the situation we had above, yes? If you allow me to go back there for just a few seconds. We had this matrix here with all exchange relations, but two of them were superfluous. So the matrix K would be this matrix. Okay, so if you have this matrix, then you can describe all polytopal realizations of your fan. Then the polytopal realizations of F are the sets of this form, or L. I'm just writing down the formula just to say that it's fairly simple and we can get all of them in this way. So each of these are L, let's say for the G vector fan in Dynkin type, each of these RL is a generalized associahedron, and all of them are realized in this way, provided that the type cone is simplicial. So that's the consequence, the upshot. If we can prove that the type cone is simplicial, then we can use this theorem and describe all polytopal realizations. But proving that the type cone is simplicial is just saying that we can find precisely big N minus small n. Big N is the number of rays, small n is the the dimension of the space where the fan F lives. If we can find big N minus small n exchange relations, so these are the rows of K, that positively or maybe non-negatively generate all the other exchange relations. So if we can do this, then we can describe very easily all polytopal realizations of the fan. And if we can do this for all finite type cluster algebras for any initial seed, then we've answered the question that the physicists asked and could find the answer to in linearly oriented type AN. So recall that this just means that the type cone is simplicial. And so maybe this is what Arnau Padrol and Vincent Pilaud convinced me of now, is that whenever I'm given a fan, I should really check whether its type cone is simplicial. And this should be in the top of my list of questions I want answered about any fan. Now let's apply this finally to cluster algebras in the last 10 minutes. It's application to finite type cluster algebras. So I want to not necessarily explain, but at least state our main result for finite type cluster algebras. And this result will tell us that first, the type cone of G vectors in finite type is always simplicial, and it will give us a way to find precisely what are the exchange relations that define it. So we have an actual description of the type cone, and therefore an actual description of all polytopal realizations for the G vector fans in any finite type cluster algebra. So let's B is Q-symmetrizable matrix of Dynkin type. If you have this, then you can organize the cluster variables in a very nice way. Just in a nice bipartite belt. You choose an acyclic seed, and you just do sinc source mutations on this seed, and you get all cluster variables, and you can organize them very nicely. So let's do this. Then one can organize all cluster variables on the bipartite belt. And let me just draw it in type A3. In type A3, you know that if you start with some initial seed that looks like this, and then you perform sinc mutations, you get all the cluster variables. So I'm numbering them pretty arbitrarily. And then if you continue, then this is periodic, of course. You go back to where you started from. So the important bit is here, this fundamental domain that contains all the cluster variables. And whenever you perform such a sinc mutation, you have a very nice relation for the G vectors. So all of these meshes are exchange relations. So this, let's say this is a mesh relation corresponding to the variable x5. This is a mesh relation corresponding to the variable x6, and so on, x8. So you get mesh relations, get mesh exchange relations, are x for all x cluster variable. And using these mesh exchange relations, you can generate all cluster variables. Okay. Now what we'll do is we'll fix a cluster C. So let's say that in our example, I choose these 3 variables. They form a cluster, a cyclic cluster. Yes. And the quiver associated to it is a 3 cycle. So I'm choosing D on purpose because this is the smallest case that could not be treated by the team of physicists or the team of mathematicians from Montreal. So you fix such a cluster C, and once you've done this, I should really now state our final theorem for this talk. Once you've fixed this cluster, you can describe the type cone for the G vector fan. So this theorem is due to the team of physicists for linearly oriented AN, is due to the team of mathematicians from Montreal for any acyclic seed, and we've generalized it for general seeds. So if you fix the cluster just as above, then the relations, the exchange relations, are x for x not in your initial cluster, positively generate all the others. Sorry, non-negatively generate all other G-vector relations. In particular, the number of facets of the type cone is big N minus small n. So in particular, the type cone is simplicial.
My apologies. Could you remind again how, for example, Rx5 looks like?
Yes. So Rx5, let me write it above. Rx5 is a relation for the G vectors.
Yeah.
And this tells you that the sum of the extreme G vectors, so let's say G2 plus G5, the G vector of X2 plus the G vector of X5 is equal to the sum in the middle, G3 plus G4.
So horizontal are equal to, sum of horizontals are equal to sum of verticals, right?
Yes, exactly. So let me write it in this way because it's important that I want to normalize it such that the two horizontal ones have +1 in front of them. So these are relations on the G vector that you can already see them in the paper of Fomin and Zelevinsky on G vectors. If you just perform sync mutations, you will obtain those. But what we can prove is that if you choose all of these mesh relations, so that's not all exchange relation by all means, it's just a subset of all the exchange relations. If you choose all the mesh relations and you remove them, you remove those that correspond to variables in your initial cluster, whatever the initial cluster is, then you have enough relations to generate all relations between G vectors for your cluster algebra. And in particular, these define the facets of your type cone, and the type cone is simplicial. Oh, I didn't finish writing the sentence. And remember that the reason I care that this the type cone is simplicial is that when I know this, thanks to theorem 2 above, I can write down all polytopal realizations of the G vector fan. So in this case, I can write all realizations of the generalized associahedra in any finite type for any choice of initial seed. So this is maybe some final remarks. So if you take theorem 2 plus theorem 3, you get all realizations of generalized associahedra. Okay. That's maybe the first remark. The second remark will sound a bit generic, but I really want to insist that this type cone approach, you can apply it to other types of fans. So can apply this approach to other fans. And they don't even have to be simplicial fans. You can deal with the fact that they're not simplicial, but it's of course then a bit more complicated. And then maybe the question that Misha asked before the talk started is what happened in infinite types. In infinite type, it's much harder to even just to decide what the correct question is. Yeah, I mean, if you take the Kronecker quiver, then what you get is a fan that is infinite, and that is you have rays getting closer and closer to this ray in the middle here on both sides. So the G vector fan is dense and getting closer and closer to this thing. And an idea that seems to work, and this is in discussions with Kani Hamed, the correct alphabetical order is Hadley Frost, Giulio Salvatori, and Hugh Thomas, is that maybe you can take a truncation of this, and then you have a smaller fan, maybe something like this. So you take 1, 2, and then you stop on this side, and then you take 1, 2, and then you stop. And this is maybe the magic ingredient, you add this ray. That's not the ray of a G vector. And when you do this, this seems to provide us with nice, interesting combinatorics and geometry. For instance, you do get, at least in all examples that we could compute, you do get a simplicial fan. You do get nice properties on the matrices, the determinant of the matrices of the G vectors for each of the cones of the fan. You get, what you do not get in general is that the type cone is simplicial, unfortunately. So this is a wide open question, I think. So we're computing a lot of examples, and we're trying to tame the infinite type by truncating it at the correct place. But as you can imagine, this picture is easy to draw for the Kronecker. If you just look at other affine types like A21 or something like this, it's not so easy to even have an idea of what it means to truncate at the right point. So with this pretty vague remark, I would like to end my talk. Thank you very much.
Thank you, Pierre-Guy. Yeah. Questions? Really, I have one. So I didn't quite understand. Well, your last remark. So with this truncation for the case for Kronecker quiver, do you have natural embedding of kind of smaller truncated into bigger truncated moduli space? Well, this. I mean,
let's see. So at the level of the fan, yes. Oh, I should have. Oh my goodness, I've forgotten a very important remark in the talk, is that the proof of the last theorem relies on categorification using representations of quivers, and this is a really important remark, because then to answer your question, if you want to look at the infinite case, if you just look at the fans and you truncate them, then you can view the truncated fan as a coarsening, as a finite coarsening of the original fan. So you can embed it into it. But if you try to look at the categorifications, I don't know what it means. I mean, you just look at some representations of very small dimension, and what do you do with them? I have no idea.
And one stupid question, because I just didn't understand. For the case A2, so can you draw this picture with these relations? Like you draw the case of A3, right? So
yes. So let me share my screen again. So you want to have, yeah, okay.
Case of A2, you need to have like three basic relations, right? Three defining relations, predefining quality. So
yes.
how?
So let's say these are the ones. Then of course, if you continue, you just repeat. So let's say you choose a cluster. I'll choose this one. All clusters look the same up to in type A2. So if I choose this one, then it's fine. Then I want to. Oh, I shouldn't have chosen this one. Sorry. With this picture, it's going to be easier if I choose this one. Then the relations that I want to keep are the ones that don't end in these guys. So this one, and this one. And what are these relations? It tells me that G1 minus G2 plus G3 is 0. G2 minus G3 plus G4 is 0. And G4, sorry, G3
Yeah, okay.
minus G4 plus G5 is 0. And if you allow me to go back to the very beginning, these are precisely
right, but
the
what
rows here.
after you factorize it? Yeah. Can you write these relations into quotient space? Well, you explained.
I don't understand the question.
You explained that you can factorize by this by G times.
Oh, right.
So it's like you can have like three in three-dimensional space, like three relations in three-dimensional space.
Yes. I'm not so good at doing this precisely, unfortunately. I'm sorry. I mean, this G of Rn is a bit complicated to imagine in R5, and then you quotient out by it.
I see.
Yeah, I'm sorry. The best we could do was this picture on the screen.
Thanks. Anybody else have a question?
So I have a question. So you were mentioning that it is based on categorifications with Weber representations. So does this, but somehow it looks like this should work also, say, for the other Dynkin types like B, C, F, and G. Yes.
It turns out that for Dynkin types, even without assuming that it's skew symmetric, so for all Dynkin types, A, B, C, D, F, G, if you're willing to use species, then the original paper of Boan, Marsh, Reinecke, Reten, and Todorov works. So you have a cluster category, even in those types. And this is all we need, because all we're looking at are Dynkin types.
Yeah, this is what I suspected.
Then if we want to go to affine types or do something different, then we're going to need something more. But at least for Dynkin types, we can live with the current state of the art in categorification.
Okay. Yeah, this was my impression. Okay, thank you.
Okay. Any more questions? If not, then may I ask to give some kind of well, to repeat your discussion with Arkani Hamet, not for the record. So I can switch.
Yes, I'd be happy to try and do so.
Okay.
A lot of students are still very